All right, let's see how this works. This is my first time trying this. 1.3, properties of graphs of functions. You'll notice that I'm not wearing a mask right now. That's because we don't have anybody in the classroom, and the custodians will be coming around and sanitizing shortly. Okay. All right, so properties of graphs of functions. The lesson itself will be pretty short, but you'll see there's a chart at the end of the lesson for you guys to complete. Okay, so we first have intervals of increase. Okay, so we're looking at where the graph is increasing or over what intervals, and then also when it is decreasing. Okay, so the intervals within a function's domain where the y values of the functions get larger. Okay, so within the x values, we're looking at where the y values get larger. And of course, when we're reading a graph, we're always looking from going from left to right. Okay, we're reading graphs left to right, not right to left. Okay, and then intervals of decrease will be the same thing, but now we're looking to see where it decreases from left to right. So erase this over here. Okay, so then something new today was we're going to learn interval notation. Okay, we will be using, it's different than set notation, which what we do for domain and range. Interval notation is something a little bit, it's new, and it's for you to list out where the intervals are increasing or decreasing in interval notation. Okay, when we do this, we use round brackets when it does not include the value, and then we do square brackets when we include the value. An example, I'll show you with the example. When we approach infinity, positive or negative infinity, we will always use round brackets because we don't know where the ending is, so we always include a round bracket. Okay, and likewise what I just said, the use of square brackets in interval notation indicates the endpoint is included in the interval. This is the same as what we did with the number line in yesterday's lesson for absolute value, where we put the closed circle if it's including the value and open circle when we do not include it. Okay, just want to increase the page. I apologize for the short, for the little glare that you have in the middle of the page, or in the middle of the screen. Okay, so example one, convert each set notation to interval notation. Okay, so there's two parts to interval notation. Is we want to list the lowest value, and then we want to list the highest value. So we want to list the lowest value, and then we want to list the highest value. Okay, so the first example is x is less than or equal to 0. So if x is less than or equal to 0, I'm just going to put it on a number line here. If it's less than and equal to, it's closed circle, okay, and less than 0, so it's going everywhere to the left. Okay, so we want to list out the lowest value and the highest value here. So the easiest one to write right now is the 0. So the 0 will be our highest value. So here in interval notation, we're going to put 0. So remember, this is the lowest value, and this is your highest value. So we're going to put 0 on the second part, and now we want to put our lowest value. Well, if this graph, it starts in 0 and it keeps going negative, 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 so negative 5, negative 10, negative 10, negative 100, negative 1,000, and so on, it doesn't end. So we don't know exactly what the lowest value is. See, since this is continuously getting more and more negative, or smaller and smaller, it approaches or keeps going to infinity. But since it's going left, it's going to negative infinity. It's because it keeps going. There's no end point to this. So we're going to put it goes to negative infinity as our lowest value. So our lowest value goes here, comma, our highest value. So lowest value is negative infinity. We don't know where it actually ends. And our highest value is 0. Okay, we don't need to write these little slashes here. Okay, so now we're going to put brackets around them. Okay, in the note above, it says anytime you're using negative infinity or positive infinity, we're going to use round brackets. So we're going to put a round bracket around the negative infinity. And if we are including 0 in our notation, then we're going to put square brackets. If it's not including 0, then it's round brackets. But going back from the question, we have the less than and equal to. So since we have the equal to here, then we will put square brackets around the 0. Okay, so that is an interval notation. So our values go from negative infinity to 0, or 0 to negative infinity. Okay, let's do the next one. So the next one is x is greater than negative 3, but less than or equal to 5. So on a number line, this roughly, we're going from negative 3 to positive 5. Okay, so we want to put our lowest value first, our highest value second. So our lowest value is negative 3. So we have negative 3. Let's use a different color. So we're going from negative 3 to positive 5, which is our highest value. Okay, going back here, we're not including the negative 3. So we have a round bracket, but we are, sorry, if I was doing number line, this should have been open, and this one will be closed. And lastly, this is less than or equal to 5. So then in our notation, we put a square bracket. Okay, so then a couple other definitions we want to go through. So first is continuous function. Okay, so this is a function that is continuous. There's no breaks or stops in the graph. So we don't have any holes or breaks within the actual domain. Discontinuous, this would have a break in the graph. So for instance, a continuous graph, so we can have a linear function that is continuous. There is no breaks or holes within the graph itself. It could be a parabola, or sorry, a quadratic that creates a parabola, so that is continuous. But something that is discontinuous would be something that has a break in it. So let's say we had a line here and then another line here. So this graph would be broken, so this would be discontinuous. Okay, often you might see ones that go like this. So down and then, sorry, down and then maybe a straight line. Okay, so if there's a break or a hole inside of the function, then it is discontinuous. Okay, odd function, I'm going to show you with an example. So an odd function is any function that, okay, so let's rewind. An odd function is where the function, if you reflect it over the x-axis and you reflect it over the y-axis, the graphs are exactly the same. Okay, so we're going to go through some of these. So if you reflect it over the x and reflect it over the y, the graph exactly the same, we call that an odd function. Okay, an even function is when the reflection over the y-axis is the same as the original function. So let's see how this would work. So if I had a quadratic and a very base function, it looks like this. If I were, so that's the parent function. So that's the parent function here. If I were to flip this over the y-axis, if I were to flip this, it would actually make the same graph. So this is the reflection over the y-axis. If it creates the same graph when you flip it over the y-axis, then it is an even function. Okay? This one here, odd, is when the reflection over the y is equal to the reflection over the x. So here's an example here. Just want to make sure you guys can see this. Okay, so a function you learned last year is a cubic function. That looks kind of like a snake. If I were to reflect this over the y-axis, so if I reflect this piece over the y-axis, it would go up this way. So if I reflect the top over the y-axis, it would go here. If I reflected this part over the y-axis, it would then go here. So this is the parent function, this is the reflection over the y-axis, which is this part here. What you learned last year is your k value. This is your k value. Okay, and then this is your a value. So then if we reflect this over the x-axis, so if I take this and reflect it over the x, so this part here reflects downwards, it would go here. If this piece got reflected over, it would go down. And then this part where it gets reflected over the x, this part would now go up. So you'll notice that the reflections are the same. So that makes it a odd function. Okay, they're different than the parent function, but the reflections themselves are the same, so it makes it an odd function. Okay, so if the reflections are the same, it's odd. If the reflection over the y-axis, which your k value, is the same as the parent function, then it's an even function. Okay, one last part is end behavior, and this is new to you guys, and it kind of gets a little bit confusing. Okay, but I'll show you with examples when we get to them. Okay, so the end behavior is it describes what happens to the x values, or sorry, it describes the values of f at x. Remember, f at x is y. So it tells you, the end behavior tells you when x goes more and more infinity, so example, say a linear equation. So the end behavior tells us what happens when our x gets larger and larger and larger, approaches infinity, what happens to our y values, okay? And then, as our x values keep going more and more negative, what happens to our y values? So the end behavior tells you as you go more and more positive, it'll tell you what the y does, and when you get more and more negative, what the y values do as well. For a linear equation, it's pretty easy. As you get more and more positive with your x's, you get more and more positive with your y's. If you get more and more negative with your x's, you get more and more negative with your y's. Okay, so I'm going to show you how to write that out. Okay, so we're going to complete the table on the following page. So you also are responsible for page 23, numbers 4 to 7. And then I'll show you from 1.3 that the table that you are doing, when this seeing here, the table on the following page, is actually number 12. So it's actually number 12 on page 25. Okay, so I'm doing this chart here. So what I'm gonna do is I'm gonna do 2 examples for you. I'll pick 2 and I'll go through all these different things. And then you're responsible to complete the table yourselves. And then after that, please go back and complete questions 4 to 7. Okay. Okay, so this is the table that's on page 12, sorry, page 25, number 12, and we have a various different functions. We have linear, quadratic, we have reciprocal, we have absolute, square roots, exponential, and then the sinusoidal, okay? You'll notice that we're only doing these in their parent function. So these are all in their parent functions, okay? There hasn't been any transformations applied. There's no shift left or right, up or down. There's no reflection over the y, no reflections over the x. And there's no any stretching or compressing, okay? No vertical or horizontal stretch or compress. Okay, so I'm gonna go through the first one. This is linear, and then I'll pick another one. We'll do this one here. This one's a difficult one, so I'll go through it with you. Okay, so a linear function. So what is the domain? So we're looking at the x values, remember, for domain, and the range is your y values, or we're doing f at x. Okay, so our domain for any linear, so these are all continuous. So we have all our negative x's and all our negative, all our negative x's, all our positive x's. So our domain is XER. Okay, so x is an element of real numbers. Okay, likewise for the y's, we have all our negative y values and all our positive y values. So we have, our range is YER as well. Okay, there aren't any restrictions because the line is continuous in both directions. Okay. Okay, so now we're going to do interval of increase. Okay, so if we read the graph from left to right, we have to see which way our graph is actually going. So we're looking from left to right. So if we read the graph left to right, it's going upward to the right. Okay, so we're going upward. So this is an increase. The graph never decreases, so this one is not applicable. There is no decrease in our graph. Sorry, I just want to rewind. Just a reminder, I told you guys yesterday, well, I'm filming this today, so I told you earlier that sometimes you won't see the y, you'll see f at x, ER. Okay, so I'm okay with the y, but you might see the back of the book, they replace it with f at x. Okay, so our graph goes left to right. Okay, so we want to do intervals of increase. So we want our lowest value and our highest value. Okay, so interval, so we're doing interval notation, lowest value and highest value. Okay, so we're looking at my x's. What's my lowest x? Well, this graph keeps decreasing, but it doesn't stop. So our lowest value is negative infinity. Okay, anytime you have affinity sign, it's an automatic round bracket. If we go to the right or positive, this graph keeps going more and more positive. Right? Our x values keep increasing. It does not stop. So it goes from negative infinity to a positive infinity. Okay, and then we round the brackets because it's infinity. Okay, so no interval decrease, it does not decrease at all. Okay, next question, is there any locations of discontinuations and asymptotes? So it's a line, there aren't any discontinuations because it's continuous, and there isn't any asymptotes, so there is none. Sorry, NA or none. Okay, zeros, remember zeros are x-intercepts. So x-intercepts is here at 0, so yes, so we have 0 at, so we have x equals 0. Okay, y-intercept, same part, same place because it's at the origin, so y equals 0 for the y-intercept. Okay, now we're looking at symmetry. So symmetry, is it odd or even? So odd or even. So you have to think which way the reflections happened. So if I were to reflect this over my y-axis, would it be same as the parent? No, it would not. Okay, so it's not a even function, but if I reflect it over the y, it'd look like this. And if I reflect it over the x, it would also look like this. So in this case, it is even. Oops, sorry, no. It is odd. It's an odd function. Okay, the reflections over the y and the reflection over the x is exactly the same. Okay, now end behavior, and I'm just gonna write it up here, just because I know where the camera is, it's low. Okay, so the end behaviors. So you need two end behaviors. You wanna know what's happening to the negative part of the graph and the positive, or I should say, you wanna know what's happening left of the graph and right of the graph. Okay, so question is, when x approaches, okay, so if I keep going, this graph keeps going more and more negative on the x's. So we said that was negative infinity. So when x goes more and more negative infinity, what happens to our y values? Well, as the x keeps going more and more negative, so does the y values. The y's also keep getting negative, negative, negative. So as x gets more negative, so it's called approaches negative infinity. So as it gets more negative, your y values also approach negative infinity. Okay, so as your x's get more negative, your y's get more negative. Okay, so that's left of the graph. Now we're doing the right part of the graph, so this side. So as my x's get larger and larger, so that it's going more and more to infinity, larger and larger. So as x goes more and more positive, or goes towards infinity, our y values also increase. So our y values keep getting more and more positive, so we say y approaches infinity. Okay, so as x approaches negative infinity, as it gets more and more negative, our y values get more and more negative. Okay, as x gets more and more positive, our y values keep getting more and more positive. Okay, just gonna stop the video here and then restart it with the next example.